Hello everyone, this is J Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equations with variable questions. So here we are going to solve the given equation using variation of parameters method. So let's get going. Problem: solve d square plus a square into y equal to tan ax by the method of variation of parameters. So we are given a differential equation of order 2, right? Given differential equation d square plus a square into y equal to tan ax. Consider it as equation number 1. Now we need to find the general solution of the given differential equation. So y equal to yc plus yp will be the general solution of the given differential equation. Now we need to find yc and yp. We will find yc using the auxiliary equation of this equation and we will find yp later. Right? The auxiliary equation is f of m equal to 0. So from this equation we will get f of d, which is d square plus a square, right? So from the above equation we will get f of m equal to, just replace d differential operator with m, will get m square plus a square. Then this equation becomes m square plus a square equals to 0, which is our auxiliary equation to our problem. Now find the roots. Just take this a square to our RHS, we'll get m square equals to minus a square. Then m equal to plus or minus square root of minus a square, which is equals to plus or minus square root of minus 1 into a square. We'll just write minus a square as minus 1 into a square. Then m equal to plus or minus square root of, now split square root of minus 1 into a square as square root of minus 1 into square root of a square, right? Now we can replace square root of minus 1 with I, since we know that square root of minus 1 is I. So we'll get, and also square root of a square can be written as, since square root of a is a power 1 by 2, right? We know this. So we can write square root of a square as a square power 1 by 2. Also we know that a power m whole power n equals to a power m into n. Then we can write a square whole power 1 by 2 as a power 2 into 1 by 2, which is equals to a power 1, which is equals to a, right? But simply we'll just cancel the square and square root, right? Which is wrong. We should not do like that. So this is a. So therefore m equal to plus or minus ia. We know that when m equal to a plus or minus ib, yc equal to e power ax into c1 cos bx plus c2 sin bx, right? And when a equal to 0, we'll get e power 0 into x, which is equals to e power 0 into c1 cos bx plus c2 sin bx, right? Since e power 0 is 1, then this becomes 1 into c1 cos bx plus c2 sin bx, which is c1 cos bx plus c2 sin bx, right? Now, so we got roots plus or minus ia. Just compare this plus or minus ia with plus or minus ib. Therefore, the complementary function yc will be c1 cos, for b equal to a, will get c1 cos ax plus c2 sin ax, right? Now let particular integral be yp equal to a cos ax plus b sin ax, or see here we are having c1 equal to yc equals to c1 cos ax plus c2 sin bx, sin ax, right? Here c1 and c2 are constants, we know that, right? So we can name it as u and this as v. Say yc equals to some c1 into u plus c2 into v. Then our yp will be au plus bv. Okay, so we'll just replace this arbitrary constant c1 c2 with a and b, which are functions of x. Again we'll find it, where u equal to cos ax and v equal to sin ax. Okay, fine. Then a and b, where a and b are functions of x, then u equal to cos ax, v equal to sin ax. If we compare the given differential equation with d square y by dx square plus p into dy by dx plus q into y equal to r, then r will be, here p is a function of x, q is a function of x, and r is also a function of x, right? Then we'll get r of x, or r equal to tan ax, right? So here, as I said earlier, we need to find a and b, right? A and b are given by formula a equal to integral minus vr by uv1 minus vu1. Here u1 and v1 are derivatives of v and u. First derivative of v, first derivative of u into dx, and b is given by integral ur by uv1 minus vu1 into dx. So before applying a and b, we'll find uv1 minus vu1 because it exists in both a and b, right? So let's find uv1 minus vu1. uv1 minus vu1. Let's find v1 and u1. If u equal to cos ax, then u1, which is derivative of u with respect to x, equal to derivative of cos ax with respect to x, which is 1 by a into minus sin ax. This is not 1 by a, which is equals to minus a sin ax. Let's now find v, derivative of v. If v is sin ax, then v1 is derivative of v with respect to x, which is equals to derivative of sin ax with respect to x. Derivative of sin ax is cos ax, so we'll get constant a into cos ax, right? Let's now find uv1 minus vu1. u into v1 is a cos ax minus v sin ax into u1, which is minus a sin ax. This becomes a into cos ax is cos square ax minus into minus plus a into sin ax is sin square ax. Since we know that, okay, just take a common from these two terms, we'll get a times cos square ax plus sine square ax. Since we know that sine square theta plus cos square theta equal to 1, we have an identity, right? Then this is equals to a into sine square ax plus cos square ax is 1, which is equals to a, non-zero, right? Now let's find a, capital A and b. I mean functions of x. Therefore, uv1 minus vu1 equal to a. Now we are going to find function of x. First we'll find a, which is given by minus vr by uv1 minus vu1 into dx. This is equals to integral minus v. V is sine ax into r tan ax by a into dx. Since uv1 minus vu1 equal to a, the denominator must be non-zero, right? So that I have written non-zero here. If it becomes 0, we'll get the integrand undefined, which is undefined, okay? But in our problem we got the denominator which is non-zero. Now we can take minus 1 by a outside the integral, then a becomes minus 1 by a integral sine ax into tan ax dx, which is equals to minus 1 by a integral. Let's write tan ax as sine ax by cos ax, since tan theta can be written as sine theta by cos theta. This is equals to minus 1 by a into integral sine ax into sine ax is sine square ax by cos ax into dx. Since we know that sine square theta plus cos square theta equal to 1, then sine square theta will be equal to 1 minus, just take this cos square theta to RHS, will get 1 minus cos square theta. Now replace sine square ax with 1 minus ax. If we replace theta by ax, we'll get sine square ax equals to 1 minus cos square ax, right? Now we'll replace the numerator sine square ax by 1 minus cos square ax, and denominator remains the same, into dx. This is equals to minus 1 by a into, so we are having two terms in the numerator and one term in the denominator, so we can split the total expression into two terms, 1 by cos ax into minus cos square ax by cos ax into dx. This becomes minus 1 by a integral of 1 by cos ax minus, here 1 cos ax gets cancelled, so you'll get minus cos ax into dx, which is equals to minus 1 by a integral of, we know that reciprocal of cos ax is secant ax minus cos ax into dx, which is equals to minus 1 by a integral secant ax dx minus into minus plus 1 by a integral cos ax dx. Since integral secant ax dx is 1 by a log mod secant ax plus tan ax plus integral constant, and integral cos ax dx is 1 by a sine ax plus integral constant. So this becomes minus 1 by a into integral secant ax dx is 1 by a log mod secant ax plus tan ax plus 1 by a into integral cos ax dx is 1 by a sine ax. Then a equal to minus 1 by a into 1 by a is minus 1 by a square log secant ax plus tan ax plus 1 by a into 1 by a is 1 by a square sine ax. So we got a. Let's now find b. B is given by ur by uv1 minus vu1 into dx, right? This equals to integral u is cos ax into v tan ax by uv1 minus vu1, which is a, into dx is equals to, write the constant 1 by a outside the integral, will get 1 by a into cos ax into tan ax into dx, which is equals to 1 by a into integral cos ax into, since we know that tan theta can be written as sin theta by cos theta. So we'll replace tan ax by sin ax by cos ax into dx, which is equals to 1 by a integral cos ax into sin ax or sin ax into cos ax by cos ax into dx. Here cos ax gets cancelled from the numerator and the denominator, will get 1 by a integral sin ax dx. Since integral sin ax dx is minus 1 by a cos ax, so this becomes 1 by a into minus 1 by a into cos ax, which is equals to minus 1 by a into a square cos ax, which is our required b. We got a and b, which are functions of x. Let's now write yp. Yp equal to a cos ax plus b sin ax, which is equals to a minus 1 by a square log of secant ax plus tan ax plus 1 by a square into sin ax into cos ax plus b minus 1 by a square cos ax into sin ax, right, which is equals to minus 1 by a square log of secant ax plus tan ax into cos ax is minus 1 by a square cos ax into log of secant ax plus tan ax plus 1 by a square sin ax into cos ax is plus 1 by a square sin ax into cos ax plus into minus 1 by a square cos ax into sin ax is minus 1 by a square sin ax into cos ax, right? So here plus 1 by a square sin ax cos ax and minus 1 by a square sin ax cos ax gets cancelled, and you will get yp equal to minus 1 by a square cos ax into log of secant ax plus tan ax. Okay, we got yp, also yc. Now let's write the general solution, which is given by y equal to yc plus yp. The general solution is given by y equal to yc plus yp. Then y equal to yc c1 cos ax plus c2 sin ax, and yp is minus 1 by a square cos ax log of secant ax plus tan ax. This is the required solution. So we have seen a problem from variation of parameters in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.